Hello, everyone. And I would like to share some work that we have been doing on traveling fires. And this is part of my doctoral work. And I've been working with Professor Simo Hostika at Aalto University here in Helsinki, Finland. So we've been trying to simulate traveling fires in FDS, and we've been using a combined approach. So we use the ignition temperature model and the single-step pyrolysis model to simulate a predictive fire. As we are using wood crypts, the ignition temperature model is for the initial fire. And the single-step pyrolysis model is for the rest of the fire load. We use an ignition temperature of 300 degrees, and the properties of wood that we use for the single-step pyrolysis model are obtained from the TGA and cone experiments. So how does a simulation look like? So this is a video of a simulation that we performed, and it's based on experiments from the BRE large-scale experimental facility at Cardington. It was done by Kirby et al. In 1999. So they had a 23-meter long compartment of 5.6 meter wide and 2.8 meter high. And they arranged 11 rows of cribs along the compartment. They ignited the first row and let the fire develop naturally. So the left end of the compartment, so the one that I'm showing with the mouse here, the mouse pointer, that's closed, and the other end is open to the ambient. So let's see how the whole thing develops. So as you can see, initially the fire started at the first row because that was ignited. So in the simulation, we modeled the first row with the ignition temperature model. So it had an ignition temperature of 300, and it had vents underneath, which acted as the burners. And once that was done, we had the rest of the wood crypts that you see in yellow or light brown is modeled with the single-step pyrolysis. And then as the oxygen is consumed, there's a rapid spread towards the opening. And then there is a slow backward spread of the fire again. So what does CFD simulation, what does it actually give us? What more information do you get? So the behavior is similar to the experiments, but we need more information. So what we see here is the oxygen concentration slices along the center of the compartment. And at 12.25 minutes, when the fire is still near the first or along the first row of cribs, you see that the oxygen concentrations along the other cribs is also reducing. So in the second row, you can see a significant yellow near the crib. So that is due to the moisture evaporating. So what the sealing and the radiation from the flames do is evaporate the moisture from the cribs in the along the other rows. And that prepares the cribs for the rapid propagation when the oxygen suddenly reduces. And as you can see, as the oxygen reduces, the fire starts to move towards the opening. This rapid spread happens in less than 90 seconds. So it's driven quickly towards the opening. And this is the effect of ventilation. Then what else do we see? Here we see the U velocity slices, and when the initial row is burning, you see a classical sealing flow. There's hot gases flowing outside and relatively cold air being entrained into the flue. But as it goes on, you see more and more turbulence. You see the effect of arranging the cribs like this. So when there is space between the fire load, you can expect a lot of turbulence in between, in the flow field. And an interesting thing that we saw is that there is a triple layered flow. So at 28.5 minutes, when the fire is moving back towards the close end, so that's the left end, you see that at the ceiling, the flow is negative. It's flowing into the compartment. Right below it, the flow is flowing towards the flame. So the flame is here. So it's flowing towards the flame. and near the crib and in between the cribs, there is this small negative velocity, and the flow is again into the compartment. So there is a three-layered flow that was never, in a sense, not seen before. So that's a new information that we get from CFD simulations. So how does it, and this is the gas temperatures that we see. Moving ahead, how does it compare with the experiments? So we see that the experiments and the simulations are quite close. Simulations do predict a lot of the experimental characteristics properly. And so the black solid curve is the experiment, and the red dotted line is the simulation. And the blue line is just for comparison. It's the ISO standard design curve. Then we compared it with the analytical iTFM, the improved traveling fire methodology, the code that is available openly. They have a MATLAB code, and we use that to compare it. As you can see, the peak temperatures are predicted very well. The iTFM model does a very good job of predicting the peak temperatures, but the far field temperatures are under-predicted. And maybe that is because they use an Alpert-Sillinger model in the analytical model. Another thing to note is that the rapid fire spread phase is actually removed from the plot, from the FDS plot, because the analytical model is not dependent on ventilation, so it doesn't actually predict the rapid fire spread. We also tested the influence of the ceiling height, and this relates with with a presentation that we had yesterday about the ceiling height affecting the smoke layer and all in the car parks. And here we see something similar. When the ceiling height is increased, the incident heat flux on the second row of the cribs reduced rapidly, and we did not see a fire spread. The same thing so here on the left side you have the incident heat flux, and on the right you have the temperatures. The same thing with the temperatures. So because the fire spread did not happen, the temperatures are quite low. So that's it from my side. A brief presentation. I can't actually hear you.
Muted, so I'm sorry about that. You have about 2 minutes for questions. If anybody has a question, ask now. Okay. Yeah, I thought that was a very interesting combination between the two, to be able to, have that ignition predict, the initial phase and then move on,
Yes.
and then use that single step back as a predictor. Kevin is asking, was the effect of char considered? Formation of the char layer?
No, it wasn't actually. You can see it in the temperature curves that because we use a burn away, the char is not actually the glowing char. The heat from the glowing char is not accounted for. So we in the extinction phase we have an under prediction.
Okay, great. We have about a minute left. If anyone else has anything. Do you have any future work to do on this? Like, what's your next step?
So we are planning to do a much more larger scale simulations using the HPC cluster here, and then combine it with structural analysis. So we'll be transferring the FDS boundary condition.
Uh-oh. Sorry about that. Got to drop out there. All right. So our next speaker, let me just go ahead and bring you in. Okay, it's coming up. There, now we see. Go ahead.
Okay. So, hello everybody. I'm Yuxin Zhang, and now I'm a PhD candidate in channel evacuation. And today I'm going to share of my some work about the information perception and evacuation decision making in different environments. And it's basically focused on two kinds of VR mode. When studying human behavior in evacuation in emergency, and we have various new methods recently to be conducted, such as strong power of modeling, such as CA models, social force models, and also we have done a lot of VR experiments, and somehow we did some field experiments now and then. But VR experiment is definitely the most popular and most mainstream experiment method, since it is economical and it's easy to change the parameters, and also it is easy for the ethical issues. And in general, the VR models are mostly focused on the lab models. That is, we design our program and rate it and install it in our lab equipment, and we recruit subjects around the campus, mostly are students, and we help them to finish the experiment with guidance. And generally, they could walk in a large room with a staff guidance, and we record their data, such as their headings, their positions, and also their movements. But due to the pandemic, the COVID-19, we are not allowed to do the physical VR experiments face-to-face. So I'm now working to try to move the experiments online. That means I write a program and I upload it to some specific VR platform. And so all the VR users could browse our application, and if they have interest, they could download the application to their equipment, and they could finish the experiment by themselves. Considering the safety issues, the experiments are expected to design in standing mode or limited movement. And I'm going to share an experiment I have done in both two ways: the standing mode and the walking mode. So the subjects are choosing two axes in different conditions. They start from here, and they could see two exit doors, either in their left direction or in their right position. And I will give them different cues, different added information near each exit to see how they follow these informations. And I have done it both in the walking mode and in the standing mode. When in the lab mode, they have to walk towards either axis to indicate they choose this exit. And in the standing mode, they just press their controller buttons from left or right to indicate their choices. And I choose 4 pieces of information in my experiment: 2 attractors, audio instructions, and exit signs on the door, and 2 repellers, traffic cone in front of the door, and another repeller as the do not enter signs in front of a door. And I have finally got some data collection, and I have done some preliminary results that I'm going to share with you. Both modes, they have some similarities. The first is the single queue following. That is, if there is one exit has a specific attractor, such as exit signs, and there is nothing in the other axis. So almost all the subjects in all trials, they are going to follow the single queue. And also, if we do put same cues, same information in either exit doors and red doors, and they will have a little preference on the red doors. However, it is somehow interesting that I find some difference during the queue competing. That is, such as if there is a traffic cone in front of the left door, and there is some do not enter signs on the red doors. And in the walking mode, the subjects will try to go to the doors with the do not enter signs in order to avoid the physical block of the cone in front of the left door. But in the standing mode, people just have to press the controller buttons, so there is no significant preference over do not enter signs than the traffic cones. And also, I try to do some calculation about their weight of 4 pieces of information during their choices, and we could see that their weight are different. And also, I have done some analysis about the consistency in choices. That means we do all the subjects will repeat each condition in 5 times, and we could see that for the walking mode, people are not that interested in their previous choices, but in the standing mode, people are likely to choose their original choice even they repeat it in 5 times. So there is a small discussion that is, since the physical block is more influential in the lab mode that people have to walk to, so will it be more influential in real world? And the second is, I'm curious, how could we adjust the weight from VR to real world, since we have maybe 2 weight parameters from standing mode and walking mode? And the last one is that, since I find that people are more consistent when choosing axis by just pressing the button rather than walking directly, does it infer that maybe decision making becomes more random in real world? So that's some preliminary discussion for my 2 experiments, both in the standing mode and the walking mode. And so I'm curious about what's the next step, and also I'm happy to share all this with you. So thanks for your listening, and I'm happy to any discussion about this problem, and also I'm looking for a postdoc position or any academic research after my graduation. So if you have some interest, you could have a discussion. Thanks a lot.
Thank you very much. We have just a couple of minutes here for questions. So you have a question here, wondering how many people are involved in the experiment and maybe their ages or gender.
Oh yes, it's a there is some difference from the subjects' age and their jobs when we recruit from the lab near the campus, and then we recruit from all over the VR experiment platform. And I have got data for either mode about 10 subjects now.
Mm-hmm. Okay.
Yeah, and so we could know that their ages are very similar in the lab mode, since they mostly are students.
Okay, and can you tell us about the country where you are running the experiment?
I'm now at the Brown University, the United States.
Okay.
And when I posted online with the VR platform, and I got more data rather than the United States. I got data from from Canada, and also I think from UK and Europe. Yeah, more variety.
Is this still open for subjects? Are you still looking for subjects then?
Oh yeah, definitely. If you have any interest, you could I will give you the link about my experiment, and we are still waiting for more data.
Yeah, maybe share links in the chat here so people can follow up and share it on different ways. So we'll be glad to share that. There's a question here about, in my opinion, or I guess a comment, you must be careful about the generalization of data as the sample size is quite limited. So just as a data thing. So, okay.
Oh, yeah. Okay.
So that's the end. Thank you very much for that talk. That's excellent. And we'll move on to our next speaker. Thank you.
Thank you.
Okay. I wanted to just share some ideas based on in response to the discussion that happened yesterday about jet fans. So this is based on some work I did about 5 years ago, which is a little bit old now. So I'm a little bit behind on current developments, but there's at least some, I think, ways forward that might help us. So the problem with jet fans, just some background, is you see this jet fan here. The entry flow is on the right. The exit flow is on the left. You can see the exhaust flow is actually angled down somewhat. The challenge of simulating it is it's relatively high velocities. The dimensions of the fan are relatively small, and we have relatively large car park enclosures, and then we have to do it for a fairly long time. So it gets pretty hard to actually run the simulation with the resolution that you want to do. Okay, so the flow regime, just talking about the challenge here. So this is a jet, and there's initially this potential core where the velocity is constant, and then we go into this axisymmetric decay region, and that's where the momentum is being transferred from the jet to the ambient air. And the challenge is actually to model that transfer of momentum, because that is what then starts to move the air through the car park or through the room downstream. And you can see that there's actually fairly good correlation between, on the right here, we have experimental data from Yuxin and some correlations that we expect to see from the jet flow. So the challenge becomes, how do we actually do this with a good mesh resolution? We start with, I just used a duct and I used HVAC, and if you divide the exit into a 2x2 grid, so you have 4 cells at the exit, you just do not have the resolution that captures that transfer of momentum to the ambient air. But if you go into if you use 20 cells on each side of the exit, then actually you start to get good correlation both with experimental results and with the expected equations. And so this exactly falls into what Randy Dermott said yesterday. When you pick your mesh size, you need to decide what is your area of interest in the flow, and then you need to have 10 or 20 divisions in that region in order to do a good capture for it. So that is really difficult because those meshes, as you saw, are 12.5 millimeters, so you just can't use those mesh sizes every place. So one thing I did try after that original work I did a while back is I did look at splitting the fan into 5 different fans and then giving radial components to the velocities exiting the jet fan simulator. And so to do that, you have to separate each of these sections that are used to represent the fan, and that is because we're giving some side velocity components, so you can only touch along edges, and you have to have set up your grid to model it in this type of way. And actually, when I did that, it started to give fairly good correlation with the results that we expect. And when I compared the results that were calculated to experimental data, so we have here 3 correlations, or we have this dashed line is the correlation to data given by equation. Here's actual experimental data from Yuxin, and then we can compare that to the calculation, and you can see the calculation actually does a pretty good job. It even does a somewhat better job of the momentum transfer than the high resolution calculations that we did. So the conclusions are this, splitting it might be a way forward to make it work. It's a hack. It's not the best. It's not as good as doing your calculations with the mesh resolution that you really want, but and it needs more validation before proceeding. But if somebody wants to work on this with me, I'd be glad to kind of pick up this work and see if it could go forward here again. The challenge is, and I really want to emphasize that if you're modeling things like a car park, you really have to demonstrate that your jet fan model is matching the real downstream flow that occurs in the car park. And that is a modeler's, you can't just go ahead and pick a resolution and say, okay, that's okay. It's not okay. You really have to spend the time to make sure you're validating your jet fan model. With that, I'm going to stop and see if there's any questions.
Thanks, Dan. Yeah, there's a couple. So one come in here. If my area of interest was more downstream of the discharging velocity, such as looking at the temperature rise of a compartment due to the supply of hot air from the jet fan, would you expect that the mesh resolution is less sensitive? Say, for instance, my main inputs are a specified CFM at a specified temperature.
I'm not exactly sure if I understand what David is asking. If the key is that you have to get the proper spreading of the downstream air that then entrains the ambient air around that fan. So, I mean, another kind of option you could do, but then it doesn't do the upstream airflow capture correctly, is you could actually have a large vent or a large HVAC exit that captures the existing spreading, and once you have that existing spreading correctly simulated, then yes, your mess resolution would be less critical.
That's interesting. And then Kevin just made a comment here about splitting the vent the way you did at the end is allowing air to be entrained into the core from the inside rather than from the outside, as you were doing with like the HVAC system. So it's a little bit better method, I think, or different method of entrainment there early on.
I'm just, you know,
and one more thing here, would inlet turbulence level matter? So on the inlet side, would turbulence there matter?
I can't answer that. I have a feeling it doesn't make much difference. By the time you're going through the jet fan, I have a feeling the flow is just caused by the motor in the jet fan.
Mm-hmm. And then Randy just asked here, can you comment on the use of a velocity patch for the area that you know, which then can be resolved with 10 to 20 cells?
Yes, I think that is an option. I think then, you know, there's so many things I tried when I was working on things back there.
I think you tried velocity patch early on.
Yes, but I didn't try a large velocity patch. I mean, it's possible you could try a large velocity patch, but then as I recall, the velocity patch, you then are messing up the inlet flow simulation into the fan, because now you have a very large area and you've got that flow. You have to capture the flow in, so you need to use HVAC, Randy. So I'll talk with you more.
Or at least some kind of geometric narrowing or something there. So, well, that brings us up here. We're going to go ahead and jump over. Simo did correct himself. If you want to continue to talk in the session chat, Dan, and answer some of these other questions, maybe, you're welcome to do that. But we'll go ahead and jump over to our next speaker. Thanks a lot, Dan.
Sure.
See you later.
Yep.
Okay, well, my lightning speech is much less technical than the previous speakers, all of which were very good. I wanted to just build on some of the material that I think Max Kinateda and Mike Kinsey and myself presented on the first day, and then I presented yesterday, and it sort of basically addresses something like a cognitive bias, or at least a change in the decision architecture that might address some challenges in fire engineering, and the discussion on sort of subject matter expertise that I raised yesterday. And that is, I guess it's addressing the problem or the suspicion that I have, especially when fire safety engineers are under pressure, that they may skip over addressing the expected behaviors of people in a particular scenario. And one trick or one device that I think is used, and I've taught it to students before, is right at the beginning, way before you get to the modeling, especially the evacuation modeling, put yourself in the scenario that you're trying to model. And, you know, what would you know in that particular scenario? What would you be doing in that particular scenario? How might you react to the information that's provided to you? What choices might you make? Now, that thought process, that analysis, if you like, may have very little bearing on the work that you're doing at that time. But what it does, if it's actually part of your engineering timeline, what it does is in your head very clearly position your work as addressing actual people and not as addressing the real technical challenges of simulating or modeling and quantifying that process. So at a very basic level, it reminds you that actually you're representing a human response to a fire situation rather than addressing an agent-based approach to it. That's a device to represent a real human response that you're interested in. Let me just share this. I've got this one slide. So let me share this. I think I can get to it. Okay, hopefully you can now see this.
Yep.
If you wanted to expand beyond yourself, you might, for instance, look at a space that you're examining, and I call this an empathy test when I teach it. but it's what might someone do. So a fire has started in the top right hand corner here, and we have a chef in the room. What might that chef know, given that he's an experienced operator? He's seen many of fires before, but he's in the room with the fire. What might he know? What information might he have access to? What might he do in response? There's me seated outside with a bottle of wine. I've drunk the bottle of wine. I'm sitting in the ballroom. What do I know? What's my status? What might I be aware of in terms of the procedure? And what might I do if an alarm sounded? We have someone here in a wheelchair. In this case, she may have a dedicated alarm notification system. She may be fully aware of all of the routes out of the space, but what impact does an event have on her and on her ability to make use of the reduced routes out of that space? And what might these two be doing here when they're maybe out on a date in a cinema theatre or something, but they're watching a film? Their attention is held. What might they know about the incident? What might they know about the response that's expected of them? And how might they behave given the people around them? So the point I was really making, sorry, let me move back. The point I'm making here is you might be able to trick yourself into thinking more carefully about what people might do in the scenarios you're looking at simply by initially thinking, what would I do? And then that automatically starts that process of, my goodness, I'm actually representing real people here, rather than dealing with the challenges posed to me by my engineering calculations, or rather just dealing with the calculations posed by the engineering calculations or by the simulation tool, which can be very significant. It's important that you always bear in mind that you're modeling something. You're modeling the fire component and the means of addressing it, and also modeling the capacity of people to respond, to make decisions and get to a place of safety. And so changing your decision architecture, as they call it, putting in this switch, this check that makes you think of what you might do in that situation, just reminds you and just starts you on that process. So I totally acknowledge this wasn't as technical as the others, but I just thought it was a device that followed on from some of the discussion that we had in the two of the presentations earlier in the week.
Great, and that's a great opportunity to kind of expand on that a little bit as well. And yeah, and I welcome any chats now, or any questions or conversation to start from that. I wonder, as somebody with, somebody with like a different level of expertise, like you might have, when you see a space, I'm sure you think of it very differently than more of like a layman, right? Like you look at routes, you look at widths, you're kind of maybe not even consciously, but subconsciously even sometimes re-evaluating an environment and thinking through these things. And
also, well, actually, Brian, I think following on from that, I look at the people, right, which may sound a bit creepy, but I don't have children, but you see your family moving, parents with the small child or elderly children, whatever. How they as individuals move will be massively governed by what the least mobile, least experienced, least capable member of that group will be. So me making a decision for myself, I can do that based on my own attributes. But as groups become more tightly knit and expanding size, so that becomes a more complex process. So that self-awareness becomes much more challenging.
Yeah, I think that's interesting, because we did see in the video footage from the stadium evacuation, or I won't say evacuation, but egress, that the mother and the child, that she held for a while and waited for a bit of the stairway to clear, because she didn't want to bring her, her little toddler right out into the middle of a flow of a bunch of adults trying to get up these stairs. So there's that consideration of timing and space and everything that's a little different depending on, what your sensitivities are.
Yeah, and you can expand the visualization, if you like, from yourself to one of your kids, to an elderly relative. And what would they do? What would they know? How might they respond? Yes, and I can see something that Anas is saying here. The initial thing is just a device to ensure a sanity check, to ensure that you you ground yourself in the understanding there's real people that you're modeling, but then you can go forwards and say, well, okay, do my assumptions and scenarios make sense based on my own internal assessment of what known individuals that I'm familiar with might do in that situation?
Mm-hmm. Yeah, excellent. All right, just seeing if there's anything else here. Yeah, so there was just a question, is there any guideline that can help people choose what behavior to use depending on the profile of people?
Well, I think that there's the new, well, not new now, but the SFPE guide on human behavior might be a good place to start, and the various chapters in the handbook, but the one by Erica Kuligowski. But I think the guide is probably a good start, and then there's obviously a whole raft of journal articles, and now I'm happy to identify some of them. But I think that the guide is probably the most authoritative document out there at the moment. I'm willing to be corrected, but certainly that's a good place to start.
All right, great. Well, thank you very much, Steve, for that, for the talk, for this, everything. It's been great having you here. So with that, I think we will wrap up and head on into the networking break. Let's see, there is just one comment here. Is there a relying on the guidance when trying to quantify human behavior danger? I'm not sure what the question is there. Kevin, maybe what you can do, Kevin, is maybe reword it here. And Steve, if you want to address that in text chat, that's great. And then we'll continue on. So we're heading into we're heading into networking break now. So feel free to get up, stretch your legs, and come back into networking. On the left tab there, click when you're ready to join and meet somebody new. So thank you. Thanks, Steve. Take care.